Hello there, let's deal with transmission and application protocols, because we also need to look at the upper half of any networking model and appreciate how the application services actually work. Now, if you're battling to follow what I've just said, we need to do a bit of a review on where we are in the TCP/IP model. So you'll recall a few videos back, we had the TCP/IP model popping up, and we've actually been working through it a bit already. But we've been working from the bottom up. In terms of where we've been working, we've looked at the Ethernet standard with the cables, the switches, etc. We've looked at the Wi-Fi standards. And there are others down here as well, but we don't have to worry about them until we start looking at something like Network Plus, or even a vendor proprietary course like Cisco CCNA. Then when we started looking at routing and IP addressing, we've dealt with the network layer, either IPv4 or IPv6. Now, in previous videos, we have discussed briefly TCP and UDP, and we've alluded to the application layer, where we're normally talking about some of the applications or programs we run on the clients, and we're also going to talk now about the things that run on the servers that make things like websites or email servers possible, as well as a bunch of other services you might not be aware of yet, but you will be soon. And believe me, there are plenty of application layer services we can talk about. But for now, let's start with the transport layer, seen as that's the next logical step as we're working our way from the bottom up. So let's talk about TCP, or the Transmission Control Protocol. Now, TCP is what we call a connection-orientated protocol. This means that the sender and the receiver are going to negotiate a communication session with each other. And in that negotiation, there's going to be characteristics and performance details that will dictate the session. One of the things I can always guarantee you when we use TCP to transport the data from the sender to the receiver is during the session setup, the weaker device, the slower device, will be the one that governs how fast we go. Now, a lot of how TCP handles all of these nice things is something called a sequence number. So when I'm transmitting something, I'm going to take the file, the data, the message, whatever it is I'm transmitting, and break it up into portions so that it fits on the network nicely. Each portion will get what's called a sequence number. It's kind of like part 1 of 12, 2 of 12, 3 of 12. You get the idea. And to achieve nice things like retransmission and all that, the recipient will acknowledge the sequence numbers. Now, what's going to happen with a sequence number is I will send you part 1 and you will acknowledge part 2. In other words, you'll tell me you're ready to receive part 2. That's how we can tell with TCP when to send something, so we don't overwhelm the recipient. But another cool thing is that if the recipient uses the sequence numbers correctly to identify and request any missing or corrupted packets, we get retransmission. So if I send you, let's say, part 5, and after a certain period of time, we call it a timeout period, you don't receive part 5, you'll acknowledge that you're ready for part 5 again. Now I'll be like, well, I've already sent you part 5. The only reason why you'd ask me to send it again is either you didn't receive it, or maybe it was corrupted by the time you got it and you need it to be resent again. Hopefully with the second time it being sent, it doesn't get corrupted somehow during transmission. So with the sequence numbering, we are able to make sure that we do something called flow control. We don't overwhelm the recipient. And we're also able to do a retransmission in the event that the first time we sent the data, it doesn't get there. We can retransmit it. Now, there's a whole lot of other things that TCP does as well that's pretty cool, but that's more of a Network Plus topic. But overall, TCP is considered to be the slower of the two, but does give you guaranteed delivery. You can be almost 100% confident that TCP is going to do its utmost best to make sure that every piece of the message arrives. And this means that we usually like to use this for application protocols that sit at the top of the model that need to have complete successful delivery. So if we use something like an email, for example, I don't mind whether the email arrives now or 5 seconds later, as long as it arrives in its full entirety. I don't want any pieces missing here. So that's TCP for us. But sometimes we want the exact opposite, and that's where UDP, or the User Datagram Protocol, comes in. UDP is connectionless, meaning that there is no session really. What happens here is the sender at most notifies the recipient that they're about to start sending stuff, and then they begin sending. It's basically a case of wake up and keep up with the transmission. And UDP will go as fast as the sender can transmit the data. Whether the recipient can keep up with the flow of data coming to it or not, that's not UDP's problem. UDP also doesn't bother with sequencing acknowledgements. If it sends it, it sends it. If it gets there, fantastic. If it arrives corrupted, tough luck. That's how UDP works. Now, this does sound kind of unpleasant compared to what TCP does, but this does make UDP the faster of the two, but it is considered unreliable. It'll send the data, but if the piece goes missing, arrives out of order, or is corrupted, UDP is not going to do anything to fix the problem. So usually we use UDP for things that are latency sensitive, and the completeness of delivery doesn't matter that much. For example, you've probably heard about voice over IP, where people basically are doing telephone calls through data networks. And the cool thing is, you don't need all the data to arrive with something like a voice over IP call to have a perfectly intelligible conversation with somebody. In fact, you could actually lose a lot of the packets, and all that would really happen is the audio quality would deteriorate. The call would sound tinnier, more terrible, harder to hear the person, but you'd still be able to hear them and be able to talk almost real time, as though it was an either traditional telephone call or the person was sitting in the room with you. So those are our two main transport protocols. There are others, but honestly, 99% of the application layer protocols are going to rely on TCP or UDP. So application layer protocols are right there at the top of the TCP/IP model. And they are usually associated with particular services that run on the server. For example, HTTP. When we talk about a web server, that's the role the server fulfills, hosting a website. The way it does that is by listening to and responding to HTTP requests. But here's the thing. There's no specific individual application that, oh yes, if you have that, it is always a web server. There's actually a couple different services that you could install on a server that would allow it to facilitate and respond to web requests, such as Microsoft's IIS, Apache, Nginx. There's a couple of others as well, but let's not get too far into it. I can install any three of those that are listed there, and that would make an ordinary server be able to become a web server. All that's missing now is the actual website I would like it to serve to people. So think of it this way. When I say web browser for the client side, you could be thinking of things like Google Chrome, Mozilla's Firefox, Microsoft's Edge, Opera, or any other number of browsers that exist. But they all do the same thing on the client side. They make requests for websites. They get the HTML source code and whatever else is necessary to render that website into what you ultimately see on your screen. And they're all using the same set of protocols. It's just a different application that engages with that. Now, because of this, we've got a standard protocol like HTTP, HTTPS, and stuff like that for web services. But we can't be 100% sure exactly what's running on the server, and frankly, we don't really care. The way we identify the application protocol we want to talk to is via something called a port number. Now, port numbers technically exist right at the bottom of the application layer of TCP/IP. You can actually argue that they live between the transport and application layer. And the whole idea is the application protocol will have a specific port number associated with it. So if I come knocking on a particular port number, HTTP uses port 80, for example. We'll talk about a couple more port numbers just now. But if I go and make a request to a web server, I make a request on port 80. That's sort of like going to room 80. And I go into room 80 and I get the service I'm asking for. It doesn't matter who's working in that room at the time. As long as I get the service I went into that room for, I'm kind of happy. I'm not too bothered by whether it was Bob or Sally who served me in that room. But of course with networking, it can't be that simple always. We have source and destination everything in networking. We have source MAC addresses and destination MAC addresses. My MAC address, the recipient's MAC address. Source IP, destination IP. My IP address, the recipient's IP address. We also have the same for port numbers. And usually in a request to a server, the destination port number is the port number that's associated with a particular service. But then, when I'm making a request, the source port number, my computer randomly picks that between 0 and 65,535. to be used as a session ID. This is what allows me to have multiple tabs open in a web browser, each tab talking to a different web server, getting a different website, all that good stuff. And at no point does the stuff in the first tab ever cross over and accidentally land up in the second tab. And that's because the source port number is acting as a session identifier. Now that's for a request. When the response comes back, everything swaps around, including the source and destination port number. Because what will happen is you'll have the web service replying to that session on your computer. It is a bit confusing, so stick with what's on the screen there. The destination port of a request identifies the service. Port number equals the service. We're good to go. And the source port number is used to identify the session in the request. We'll double down on that detail properly in Network Plus. So these port numbers kind of matter, right? Now, there's a bit of good news, bad news with port numbers. And because I'm a little bit of a pessimist, I always like to start with the bad news so that the good news sounds better. So the bad news is you have to memorize port numbers and the associated protocols that go with them. That's the bad news. The good news is there's 65,535 port numbers. If you're wondering how's that good news, you don't have to memorize them all. Okay, that's not too bad. Bit of more bad news though, because hey, let's balance the universe with some bad news as well. The list that you need to remember will get longer with every certification course you do. So right now, considering that you're looking at doing A+, the list is probably about as short as it's ever going to be. Damn. Good news though, if you were to forget some of these port numbers between A+ and whatever exam you decide to do next, it's going to happen, but you're going to have to just relearn it when you do that one. And honestly, if I was part of the hiring process and you couldn't remember a port number and needed to look it up, I would be okay with that personally. I would rather have somebody go and double check themselves and get it right than try and show off how well they can memorize some arbitrary detail that we can easily go and look up on Google or any other respectable search engine. Nowadays, it's not so much about what you can store in your brain, but more a case of, can you use that knowledge? So that's a little bit of good news. And any place that you would want to work at should hopefully have the same perspective of port numbers. But we do kind of expect that some of them will stick in your mind with just sheer repetition. And that's the final bit of bad news. You're just going to have to memorize this. I've got no easy tricks to memorize these things. But what I do know that helps is knowing the ranges of some of the port numbers. So port numbers that go from 0 through to 1023. These are referred to as common ports. I've seen some other terms to describe this range, like the open standards and stuff like that, but these are some of the common open standard protocols you'll often see. Like, for example, HTTP is a pretty well-known protocol service, and that obviously sits in the common range. But then after that, we get port numbers 1024 to 49,151, and these are referred to as registered ports. Now, quite often, registered ports are registered to a specific vendor, often for a vendor proprietary protocol. However, what's been happening a lot over the last several years is a lot of vendors have started making their protocols a little bit less proprietary and a little bit more open, because open standards in networking are awesome because it guarantees vendor interoperability. And then from 49,152 to 65,535, we call these the unregistered ports. I've seen some people call them the private ports, and that's kind of okay to call them that. But what effectively happens with that range is those port numbers are not formally assigned to any particular application or service. They are, however, used. Usually when a vendor is developing a special proprietary protocol, they will probably have it running on one of those ports in that range temporarily until they get their formal assignment of that port number for their proprietary service. Now, when it comes to studying for port numbers, I'm going to give you a bit of a tip here. Always check the course's exam objectives for any application service protocol and check to see if there's any associated port numbers with them that you want to memorize. Never trust any training material, including my own, to be perfectly comprehensive and cover every single protocol and port number. Double check with the vendor. If they specify an obscure protocol that I forgot to mention or I don't believe is valuable to know, but you might get a question in the exam that asks, what port number does this obscure protocol use? That might make the difference between you passing or failing. So double check every content creator, textbook, course resource, studying resource, whatever, and go to the exam objectives published by the vendor who make these exams. At the end of the day, their objectives documents are the ultimate authority of what could or could not appear in the exam. Now that tip and advice out of the way, let's talk about the well-known port numbers. So here's the list of port numbers that you should probably need to remember for your A+ exam. So here's the first table. I'm going to bring up a second table just now. One of the main challenges I think a lot of people have learning these port numbers is we try and learn them in numerical order. And that is sort of okay, but sometimes we need to jump ahead and then jump back. Sometimes we need to jump quite a lot of numbers to talk about protocols that are closely related. So I'm going to be doing kind of a mix of both, where I'm going to start out numerically, but I'm going to jump around occasionally. So just bear with that. Now, the first one that you're interested in remembering is the File Transfer Protocol, or FTP. This is a TCP-based protocol, worth memorizing, but I would worry about application service, port numbers first, and then transport protocol it uses as a, hey, you've got a bit of extra mental capacity to remember that. If you don't remember this column here, that's okay. I'd rather you remember this and this. All right, where was I? FTP. So with FTP, it's got two port numbers associated with it. The one port number, 21 in particular, is used to do control, and port 20 is used to actually move the data around. FTP is a really, really old protocol. In fact, it was one of the original protocols to ever be used on the internet, and its whole job is what its name sounds like. It's all about moving files around across a network. And a lot of the older TCP protocols used to get two port numbers associated with them. Hence why FTP's got two port numbers, and a couple of these other ones only have one port number. They were a little bit newer. Now the next one that you'd be keen to know is port 23. Now I want to do port 23 first because Telnet came out before Secure Shell, or SSH. So Telnet, thankfully that's the full name, was one of our first remote administration protocols, giving us the ability to remotely access and administrate another device, whether that device be a router, a switch, a server, whatever. But there's a big catch with it. Well, a couple big catches. First one is Telnet does remote command line administration. There's no remote graphical user interface. Everything through Telnet is done through commands. So that means you need to be comfortable with the commands that the system you're remoting into with Telnet uses. Now, as you progress through your IT career, you're going to get exposed to more and more commands, and believe you me, you're going to like commands eventually, because sometimes you can get way more done with a couple commands compared to what you could do through a graphical user interface. So whenever you do get exposed to the command line for any operating system or platform, don't be afraid of it. But there's another problem with Telnet: a lack of security. Now, the lack of security is actually the encryption on the message. Telnet does allow us to authenticate somebody, so username and password, before you connect to something, but after that, there's no real big protections, because every packet sent through Telnet is sent in what we call clear text. No encryption. If me or an attacker are able to intercept the packets that make up a Telnet session, we can look inside and see exactly what you typed, or exactly what's being sent back to your computer screen, which is kind of scary. And sadly, the way Telnet was designed, there was no way to easily add encryption to it. A lot of the other protocols we talk about, you'll often see a variation with an S at the end, indicating it's a secure variant. But Telnet just couldn't have that security added, which is why a complete new alternative called Secure Shell, or SSH, was developed. Now, for a weird reason that we're not going to get into here, SSH got a numerically lower port number, despite being the newer thing. Now, Secure Shell does exactly what Telnet does, remote command line administration, but it does so securely with some pretty good encryption. And in fact, SSH has been so well designed that we can use it to encrypt other protocols and services. The downside, though, is the setup to get it to do that is kind of hectic, and definitely outside the scope of A+. Then we've got SMTP, the Simple Mail Transfer Protocol, and it runs on port 25. SMTP is referred to as the outgoing email protocol. So when I'm using an email client on my computer and I draft an email and I hit send, As soon as my mail client starts contacting my mail server to get that mail to your mail server, SMTP is used to do that. But once an email is on your server, SMTP is not what's used to deliver it to your client application so that you can read it. So now I need that second table, because POP3, or Post Office Protocol version 3 on port 110, or IMAP version 4 on port 143, those two are used as delivery protocols. Now, either one can be used, and both can be set up on a mail server simultaneously, but the client will use one or the other to download. The reason why we have two is POP3 relies on the client connecting and syncing to check if they've got any new mail that they need to bring in. Whereas IMAP 4, a notification, it's called a push notification, gets sent from the mail server to the recipient's client application, triggering it to synchronize. That's the main difference between these two protocols. But they are considered our delivery protocols. They get it from the recipient's mail server to the recipient client device so that the user on that client can read that email. Now, back to this list, because the next one you want to know about is DNS, or Domain Name System. We're going to talk a bit more about DNS later on in this video. So the basics is, it's the service that resolves names to IP addresses, and it runs on port 53. Now, it's one of the weird kids that uses UDP and or TCP. Generally, DNS does favor UDP, but some of its activities and operations can run through TCP. But for all intents and purposes, consider it a UDP protocol. Then, another protocol we're going to talk a bit more about later in this video is DHCP, Dynamic Host Configuration Protocol. Its job is to make the allocation of IP addresses and other IP information to clients a lot easier to do. And it has two port numbers, port 67 and port 68. The reason for both is client port number, server port number. And it uses UDP exclusively because until a client computer gets an IP address, it's kind of difficult for that device to do TCP communications. But UDP can do it all day long. Then onto a port number I definitely would hope you remember is HTTP, or the Hypertext Transfer Protocol. This protocol's job is to move the HTML files that define a web page and any other resources for showing you a web page from the web server to the client that wants to see the website, and it runs on port 80. Nowadays, with web browsing, we are very security conscious, and a majority of websites you go to nowadays will actually direct you to use HTTPS, or basically Hypertext Transfer Protocol Secure, and that usually runs on port 443. And it uses, again, a pretty good form of encryption that's able to keep most of your communications reasonably safe and protected from threat actors. Please understand that encryption is not bulletproof. We'll talk a lot more about encryption in some topics in A+ Core 2, but the short takeaway you want here is this. Any encryption can be cracked eventually with enough time and processing power being thrown at it. But as long as it stands up long enough, it'll do me good. Think about it this way. If I can intercept the packet that contains your password, and I can crack that encryption in an hour, that's not very good. But if it takes me a decade to crack that encryption, I'm probably not going to dedicate 10 years worth of compute time to try and bypass your password, because by the time I get it, you've probably changed your password. Or at least I hope you have. So as long as the encryption stands up long enough, we're all happy. Now, I already did POP3, so I can jump now to doing NetBIOS. NetBIOS is a legacy naming and sharing service protocol created for Windows many moons ago. And it runs through port 137, 138, and 139. It's kept around for legacy purposes and what we call workgroup and home group communications. But nowadays, we generally prefer something like SMB, or Server Message Block, running on port 445. Again, it was originally created by Microsoft, but it is available for other operating systems like Unix and Linux. And it's used to facilitate shared folders and shared network printers, at least in a Windows ecosystem. So generally, you'll see SMB used a lot more nowadays than NetBIOS. But it still hangs around because Microsoft does have to support legacy things, because obviously Microsoft knows that there are organizations out there that for whatever rhyme or reason have to run an old version of Windows. Please don't judge them too harshly. At some point, we're going to have a conversation about why legacy is the thing. Then again, because I jumped around, I skipped over LDAP, or the Lightweight Directory Access Protocol, which runs on port 389. Now there is an encrypted version called LDAP-S, but you only have to remember that one for Network Plus onwards. But what LDAP does is it allows us to run something called a domain environment. So enterprise environments usually use a server called a domain controller to control, coordinate, and administrate the clients and other servers in an enterprise environment. It's considered a bit of a force multiplier because it allows a relatively small IT department to administrate a significantly large number of users. Without a domain controller, there would be this linear relationship between the number of IT professionals you need to support a certain number of users. So for example, if we needed one IT professional for every 10 users, I can guarantee you it's going to be a factor of 1 to 10. But with LDAP, I could have 1 or 2 people easily supporting 10 to 1,000 users, and the workload wouldn't be that much more significant overall. Now, in terms of how this is going to work out, the clients and the servers that are part of the domain need to be able to talk to the domain controller to figure out who's who, what's what, and how to control the access and security. And the protocol that's used to facilitate those queries is the Lightweight Directory Access Protocol. We'll talk a bit more about domains and how domains work in later videos in the series, as well as in other courses from CompTIA. We've already done HTTPS, I jumped ahead to SMB, so the next one that you're interested in is RDP, or the Remote Desktop Protocol. That runs on port 3389, and the reason why we suddenly jumped into that registered range is because Microsoft created the Remote Desktop Protocol, originally for Windows to Windows only. And I don't trust CompTIA to be correct about this in the exam, so for the exam purposes, just go Microsoft Windows only. But Microsoft has been opening this up to other operating system platforms. A bit of cool insight for you that might be nice to know about for the workplace. There is a version available for Linux called XRDP, where we can actually use Microsoft's RDP tool to remote into a Linux machine, or vice versa, a Linux machine remoting into a Windows machine. It's pretty cool. But when these proprietary services change, CompTIA is often a little bit behind on this. And I don't mean this in a nasty way. It just is the way CompTIA is. So for now, just assume in the exam and for your studying purposes it's Windows, but in the real world, don't be surprised if you see RDP on a non-Microsoft platform. Now for DHCP, a pretty cool application service that makes network administration a hell of a lot easier. And believe you me, even on your home network, I can guarantee you DHCP is rocking, because you probably did not have to statically or manually assign an IP address on your home network. It just worked. So DHCP is a server role that will be able to allocate IP address information to clients that request it. The IP address information that gets given out is a unique IP address for that client that hopefully no one else in the network has, a subnet mask to go with it to define the network and host address portions, the default gateway for that IP subnet, so if somebody needs to get traffic routed to other IP networks, they know exactly who to forward it to. And then the fourth piece of information is actually categorized as additional information. If you were expecting me to say DNS, you were kind of right. The DNS server address that you want to talk to resolve names to addresses is one of those additional pieces of information that a client might say, yes, please, I'd like to know that. But there are other pieces of information as well that DHCP could provide. Now, I don't want to get into that in this course. I'm going to save that for other courses rather. But just keep that nugget of information in the back of your mind for the future. But the goal of DHCP is, as I said, it makes life easier because we can use it to allocate IP addresses to client computers. Whether it be in a small office, home office environment or an enterprise network, it just makes life that much easier. Often though, the fixed devices in our network, like printers and servers, will usually favor static IP addressing, as those devices are not going to be coming and going regularly like a user's laptop or smartphone. If we do want those devices to get addresses from a DHCP server, I might use something called a DHCP reservation to give more certainty that a server or a printer will always get a particular IP address. But how does it work? So first of all, you will be having to set a server up. Even your home router has a little mini DHCP service in it, where that server has what we call a pool of addresses. Effectively, it's just a range of IP addresses from a particular subnet that we've decided we want to use in our LANs. Very strong probability if you're on a home network right now, 192.168.0. something is a very popular pool that's used on SOHO routers. but others might be used as well. And you can always change it if you want to be a bit different, but please stick to those private networks I taught you about in a previous video. Now, the process that DHCP goes through is kind of cool. What will happen is the clients will start out with no settings and information. So the only thing they can really do is a basic broadcast. And they send that broadcast out onto the network asking if there's a DHCP server present. This is called the discover phase, or the discover message. And if there is a DHCP server present on that network, that server will respond with an offer message. That offer message will contain the IP information, like the IP address the server is willing to give you, the subnet mask, the default gateway, and basically what is a menu of the optional information. This is referred to as the offer message. When the client gets that, they will make a request of that IP information. The way the request works is the client is saying, hey, I want to use that address you're offering me. Please book it out for me so that no one else gets it. And obviously I'm going to use that default gateway and subnet mask that comes with it. And I'd also like the following additional information. Now, if the client's like a laptop or something like that, it's probably going to ask for the DNS server. And then the server will respond with an acknowledgement saying, cool, you can use that information, you can have that address and all of that, and here's that extra stuff you want to know. Now, the way to remember this exchange is DORA, D-O-R-A. Possibly related to Dora the Explorer, I'm not quite sure. Now, the address is allocated to the client, but it's allocated for a period of time. It's a lease duration. The client doesn't get the address forever. It's going to get it for a period of time. Exactly how long? Well, that will depend on what's running the DHCP service. Some OSs and services that you can install to run a DHCP server will give out an address for 8 hours. Others might give an address out for a day. I've even seen up to a week as a default setting. But you can always adjust that if you're not happy with that lease duration. Now, there are some extra cool things that you can do with DHCP, like, for example, a DHCP reservation. What happens here when we do a DHCP reservation is I'm telling the DHCP server, here's an IP address in the pool that I would like you to set aside for a specific client. And the way the DHCP server will know which specific client must get that address is usually we'll tell the DHCP server, here's the client's MAC address. So if you see a discover message coming from that MAC address, because that thing I can guarantee you the client will always have, the DHCP server is able to go, okay, I've been told this person must always get this IP address from the pool, so I will only give it to that person. So that's one way to guarantee devices always get a particular IP address from DHCP. Another cool thing we can also do with DHCP is something called a DHCP exclusion. What this does is it tells the DHCP server, please don't give out certain addresses within the pool. Because usually most DHCP services work with a start and end address for the pool. You don't specify every single address in the network because that could take ages. With a Class C network, you've got up to 254 addresses. With Class B, you're looking at 65,000 odd. And with Class A networks, you're looking at 16 million. You do not want to allocate those addresses manually, either within a server or statically, because that's just a lot of typing to do. So most servers say, give me the start and give me the end address for the range of addresses you want to give out. But if there's some addresses in the middle that you want to keep aside for maybe static assignment, you set up a DHCP exclusion. Now, if you want to learn more about DHCP, you can either play around on your home router, just be careful with the settings, or you could go and check out some of my videos in the Network Plus series. But now let's move on to DNS, or Domain Name Services. This is another super awesome service for your network, because its job is to resolve various types of names to IP addresses. I mean, think about the number of people that you could potentially phone right now. How many of those people's numbers do you know off the top of your head? 1, 2, maybe half a dozen. But after that, you're going to be relying on your contact list, right? But your phone is not dialing that person's name when you call them. Your phone is dialing their phone number. So DNS is effectively like your contact list, but for IP addresses on networks and especially the internet. Now, DNS can resolve various parts of a name, such as the host name or the domain name. And if we combine host name and domain names together, we've got something called the fully qualified domain name. So let's dissect this. CompTIA.org is a domain name, and any server or client within that organization that's internet or publicly facing will usually have that as its domain name. The web server that you're contacting to look at CompTIA's website is called www, and we consider the whole string there to be a fully qualified domain name because we're identifying we want to talk to the web server. Not the mail server, not the FTP server, the web server specifically. And we want to speak to the web server in CompTIA. CompTIA is an organization, not a commercial company. Hence why we say .org, not .com. But if you do type CompTIA.com, it's going to redirect you to CompTIA.org anyway. I'm going to tell you now how that works. But what I've just described there, with a fully qualified domain name, the kind of thing you'll type in the URL bar of your web browser, that's usually going to resolve names on the internet. And we're relying on public DNS servers to do that. You can run private DNS servers on a LAN if you want to. Now, on a small office, home office network, this is not very common to do. But in an enterprise environment, yeah, you can see that happening because maybe you'd like LAN users at the office to be able to resolve names of internal servers to private IP addresses. So you can run a private DNS server for that. But I would not completely exclude public DNS because people at the workplace obviously do need to go on the internet and communicate with various sites and services there. So a combination of public and private is often used in most enterprise environments. Now, the beautiful thing about DNS and the domain namespace on the internet is there's actually some hierarchical organization to it. That dot in a website's name, like for example, CompTIA.org or Microsoft.com or something like that, that dot between the name of the site and the com, org, whatever, that's called the root point. And there's a couple of DNS servers on the internet called root DNS servers. A couple of popular ones are 1.1.1.1, which is operated by Cloudflare, 8.8.8.8, which is operated by Google. Those are root DNS servers. Now, the funny thing is, those root DNS servers don't know about CompTIA, YouTube, or any other organization for that matter. They know about things like the com portion, the org, the net, possibly the country codes like UK, which is why you might see .co.uk. It's basically the UK version of .com. And .gov.uk, the UK version of .gov. So you might get these country-specific codes being used quite a lot. It's quite nice if you want to indicate exactly where in the world a particular site is or where this business operates. Now, these are referred to as your top-level domains. Com for commercial businesses, orgs for charities and non-profits, net for various things, often ISPs use .net, country codes to indicate where in the world this entity is. Helpful for some things because if I am looking for a plumber, I don't want to see plumber.com because I've got no idea where in the world they are. I'd like to see plumber.co.country code to know whether they're going to be any good to me or not. Then you'll start to come down to lower level domains that will deal with the authoritative answer for, okay, who is YouTube? Who is CompTIA? And resolve those domain environments. Obviously, these names you have to pay for because you want to be unique on the internet with your name, not just your IP address. And then within this domain, you will get your actual host name, like www for the web server, or smtp.comptia.org for the sending mail server. So you can see why it's worth knowing your application protocols, because they're often going to fall in the host name for publicly accessible services. So that's an idea of your DNS hierarchy. No single public DNS server knows all the answers. The root DNS server knows the top-level domains and looks at the .com, the .gov, the .org, the .whatever part at the end of the name. And then, for example, .com will know about YouTube versus Microsoft versus whoever else is a .com, and get you to a DNS server that will give you a more authoritative answer for the individual hosts within those domains. It's a very elegant and cool solution. But that's just the servers you talk to. The servers keep records on them. Now, there's different kinds of records to deal with different kinds of names you want to resolve. For example, you get something called an A record, which resolves the name for an IP version 4 host. If the host is using IPv6, the record type is a quadruple A record. AA and AAA are batteries. I know it was a terrible joke. Then, another type of record you get is called a CNAME, or a canonical name. The idea of a CNAME is I might go and register a secondary domain name and want that name to point to my actual name. So, for example, a lot of people are in the habit of typing an organization's name .com. I can guarantee you, at least one of you watching this video has typed CompTIA.com, not CompTIA.org, if you've typed the domain name into your URL bar of your browser. And that redirects you to CompTIA.org. One way to do that redirection is a CNAME registration. Quite helpful to minimize on people accidentally navigating to a slightly incorrectly typed domain name. Then you get something called an SRV, or a service record. Now, service records are kind of interesting because they're designed for applications where they're going to search for a particular service that might be running on your server, but you don't get a say in the name you give your service. If the vendor who developed the application wants the server to be called Billy Bob Jill, it's got to be called Billy Bob Jill. You've got to register a SRV record for Billy Bob Jill that resolves to this particular IP address. Then another kind of cool record is something called an MX record, or mail exchange record. If you send an email to me, you don't care whether my mail server is smtp dot whatever, pop3 dot whatever, imat4 dot whatever, or anything else dot whatever my domain name is. You just care, is this the mail server that I need to send traffic to get an email to this person? So instead of having to figure out exactly which host you need to speak to deliver a mail, you can say, hey, DNS, do you have a mail exchange record where I can send an email? And this IP address should be the authoritative primary mail exchange server for this person or organization. So that's the idea of an MX record. Instead of having loads of records for email servers, you just have one big one that covers every potential protocol and service that could be used to facilitate emails. It's pretty cool. And then you get TXT records, or text records. Originally, this was just an ordinary text file that was there for administrators to leave little notes for themselves. You'd be surprised how helpful that kind of thing can be. But over the years, security professionals have co-opted those simple, kind of unused TXT records for things like Sender Policy Framework, Domain Key Internet Mail Exchange, or DKIM, and DMARC. All three of which are used to try and validate the legitimacy of an email sender and minimize on spam and report on people trying to maliciously use your domain for their spams and scam attacks that they're doing against people. Now, personally, I believe that CompTIA should have left this for a later course like Security Plus. But hey, here we are. They get mentioned in the exam. But at A+ level, you just need to know that SPF, DKIM, and DMARC are there to help enforce email security by allowing the recipient mail server or even the recipient client to be able to validate certain details and records against TXT records on an authoritative DNS server for the supposed sender of that mail. And yes, you can have protocols working together that don't seem to immediately have a relationship. For example, when people learn about email protocols, they often don't think, could DNS be part of this? Well, in the case of SPF, DKIM, and DMARC, yeah, it can be. But please don't stress too badly about learning everything about SPF. You'll see more about it in Network Plus, but especially Security Plus and beyond, where you would be expected to know more about it and have some insight into how to set it up. At A+ level, just knowing what it is enough. Now, this has been quite a long video for some application services, but hey, this was kind of important to work through some of these topics. So obviously, thank you for watching this. I really appreciate you sticking with me on this, and this is going to lay a really good foundation for your career going forward. Although you might not be enjoying networking that much, I promise you it is a big deal. Whether you want to pursue networking further or you want to do something else in IT, networking is going to become part of the conversation at some point. Even developers, much to their dismay, need to become better at networking than they used to be. Nonetheless though, as I said already, thanks for watching, I really do appreciate it. And if you have any friends, family members, or peers that would also like watching and learning A+, don't be afraid to share this video with them. Otherwise though, I'll catch you in the next video.